right, ladies and gentlemen, welcome back to another HL chemistry lesson with Mr. Kenton. Hope you guys are doing well today. So we're moving through our first topic, which is stoichiometric relationships. Last topic we were looking at really matter, properties, changes, very simple stuff. All of this I'm imagining is a review for all of you, but I want to make sure that we've got these things down, because if we don't, then as we move forward, those concepts are not going to be as easy to grasp as we need them to be. So I apologize right now if you're bored. We will get into some cool stuff eventually, but we got to make sure we have the foundations that are there. And so we're going to be looking at the mole concept today. Now, again, can't take credit for the slides. Got to give credit to Miranda Sawtelle from Alameda International Junior Senior High School in Lakewood, Colorado. So just trying to cite my sources so I don't copyright infringe or take anybody's property unknowingly. All right. So what are we going to be looking at when we start to look at the mole concept, which for us, the mole, as we're aware, is a really big deal. It's pretty much essential to our understanding of chemistry, is how we work with and use the mole to make different conversions and to move between different substances. Now, we should be able to recognize that the mole makes it possible for us to correlate the number of particles with the mass of the substance that can be measured. Right? And so particles, we start to think about them. There's lots of them that make up the substances we interact with. We don't really understand it at that particle level, but when we convert it to mass, we understand that. So moles allows us to go from that particle level to that macroscopic level that you and I can better comprehend and grasp. Now, when we start to look at the mole as a concept, it was developed from the related concept of equivalent mass in the early 19th century. Now, again, with IB, we want to think about how does this particular topic, how does it give us international mindedness? How does it correlate and relate to things that are going on globally, not just simply here in the United States? And so we think about the SI system, refers to the metric system of measurement that's based on 7 base units. Okay, and so again, we talked about in the last couple videos of just how science has a way for us to be able to communicate across different languages, right? And so having the same system of measurements allows us to do that. We've also got the International Bureau of Weights and Measures. Can't say I've ever heard of this one, if I'm being totally honest, but it's an international standards organization which aims to ensure uniformity in the application of SI units around the world. Sounds kind of crazy. Now I just kind of envision somebody who works for, I'm going to call them BIPM, and they go to a science lab and maybe the lab is using non-standard units or something, and then it's like they report them to some sort of higher power and they then get cracked down on. It's like the unit police, if you will. That's what it sounds like. That's how they're making this sound. So, but it makes sense, right? So in terms of scientific collection of data, we do want to make sure that there is this uniformity, this consistency with using these units, right? Because it does allow for our communication, our dialogue, and our conversations to be much more consistent and possible across different languages. Doesn't mean it's always the best thing, but in this particular case, it's definitely going to prove to be beneficial for scientists across the world. Now, bringing in TOK, so theory of knowledge. So I want you guys to consider, and we're probably going to look at this question as a warm-up, the magnitude of Avogadro's constant is beyond the scale of our everyday experience. I mean, you think about it, 6.02 times 10 to the 23rd. I mean, that's just a monstrous number, right? And so for us, like where we are, it's hard to fathom what that actually means. And so as you consider that, or you could even think of just the concept of infinity, right? How does our everyday experience limit our intuition? How does our everyday experiences prevent us from being able to relate to something that is maybe a little bit beyond what we typically deal with? So again, we'll probably see this as a warm-up question, but just again, consider that as you're thinking through this. Now, our first big key idea that we're going to hopefully gather from this particular section is that the mole is a fixed number of particles, and it refers to the amount of substance. And remember, moles is commonly abbreviated with a lowercase n. So that's what we're hopefully going to move into as we start to look at these notes. So when we start to think about matter, we talked about how they can be pure substances, they can be mixtures, and then within our pure substances specifically, we can have elements or compounds, right? And so when we start to look at chemical species, specifically those pure substances, when you're looking at elements and compounds, if you're dealing with an element, it's going to be an atom. But if you're dealing with your compounds, then you're going to be dealing with something that's either a molecule or an ion, depending on the type of bonding that that particular substance is demonstrating, whether it's ionic or covalent. Now, this is the same as using the terminology that particles refers to atoms, molecules, and formula units, okay? So just kind of know that's where we're moving to here in this particular discussion. And remember, if you've forgotten, formula units, that's the term that we use to refer to ionic compounds when we start to look at them at their smallest particle level, right? Formula units are made up of ions. And so hopefully that's making sense thus far. Now, when we look at the definition of the mole, like if you go and you had to look at a textbook definition, it would say that the mole is the amount of substance that contains the same number of chemical species, particles, as there are atoms and exactly 12 grams of the isotope carbon-12. Okay, that is the exact definition of that, because for scientists, what they did is they picked a standard isotope and they used that, they determined the number of particles in that, and then they based everything else off of that particular reference isotope, if that makes any sense. Which is pretty fascinating. Now, when you start to look at that, you could say, okay, well, the mole then is always going to be relative to carbon-12. And so if we ever decide to change that definition, if it's no longer based off of carbon-12, then it might shift the scale a little bit. That hasn't happened, at least to my knowledge at this point. And so for now, we can keep using this as a particular reference point. Which leads us into Avogadro's constant, L. Now, this has the value of 6.02 times 10 to the 23rd particles per mole. And so if we tie that back to the definition of the mole, what we're saying is that carbon-12 had 6.02 times 10 to the 23rd particles present in exactly 1 mole. Should make sense. And then we can start to apply that to all of our other different substances, that no matter what it is that we're dealing with, if we have 1 mole of a substance, we should have 6.02 times 10 to the 23 particles. Whether it's atoms, whether it's ions, whether it's molecules, whether it's formula units, whatever it is that we're dealing with, that's the number we're going to have as it relates to Avogadro's constant, or Avogadro's number, as you've probably commonly heard it referred to as. Now, I think you guys have heard me say this before. Your other chemistry teachers might have said this before. The mole is essentially the chemist's counting unit. This is how chemists keep track of the amount of substance that we're dealing with. And the mole is pretty much universal. It helps us move between different particles of the substance, different units of the substance, or it can even help us move into different substances altogether and figure out quantitative information. So like we know, it contains 6.02 times 10 to the 23rd particles of whatever that substance is. And so a good analogy would always be like this idea of a dozen, right? When I say a dozen, we automatically know that I have 12 of whatever that item is. And honestly, if you guys are like me, when I hear a dozen, I think of donuts, and it makes me want Krispy Kreme. But I digress. So when you hear mole, what should automatically come to your mind is, okay, someone just said a mole. That means I have 6.02 times 10 to the 23rd of whatever that thing is. It could be, like I said, it could be atoms, it could be molecules, it could be something that's outside of things like that. Like if I said I had a mole of photons, that would mean I would have 6.02 times 10 to the 23rd photons, right? Or if I had a mole of bricks, that's a lot of brick, that'd be 6.02 times 10 to the 23rd bricks. Now, what are these species particles that I'm talking about? We've got atoms, which are going to be our smallest species of an element, right? Those are specific to elements. So those are going to be things that are found directly on the periodic table. You've got molecules. So this is the smallest component of a covalent compound. So like if you think of carbon dioxide, for example, if you had one molecule of CO2, so one carbon atom and two oxygen atoms, and they were chemically combined, that would be your molecule of CO2. You've got ions. These are the smallest species of an ionic compound. So again, if you were to take a look at an ionic compound and you were to break it down into its smallest components, like sodium chloride, for example, that would be having the one sodium ion and the one chloride ion. Now, when we want to count atoms or molecules, we use Avogadro's number as our conversion factor. And you guys should be pretty familiar with conversion factors. And so there are 6.02 times 10 to the 23rd number of atoms in 1 mole of any element that we're dealing with. Or if we're talking about molecules or compounds or formula units, there are 6.02 times 10 to the 23rd number of molecules in a covalent compound. All right, shifting gears here. Masses of atoms are compared on a scale relative to carbon-12 and are expressed as relative atomic mass and relative formula and molecular masses. Okay, and so we're going to be diving more into this idea of the relative nature of carbon-12 and how we're using that moving forward. So we're going to go through some definitions that we're probably familiar with, but you've maybe never heard them phrased this way. So you've got relative atomic mass, which is abbreviated AR, is the average mass of an atom. And what that does, it also takes into account the relative abundances of all the naturally occurring isotopes of the element. So when you start to think about when you look at the periodic table, and like you look at carbon, for example, and you look at its mass and it says 12.0108, like it says on my periodic table, what you're looking at is what we should really be deeming the relative atomic mass. Okay, because what we're doing is we're taking into account all of the relative abundances of all the naturally occurring isotopes of carbon. So not just carbon-12, but carbon-12, carbon-13, carbon-14, and whatever other carbon isotopes that we have. Hopefully that makes sense, right? Then you've got the relative molecular mass. And so essentially what you're doing there is you're going to be taking the sum of the relative atomic masses within that given compound, this covalent or molecular compound, and you're adding them together, right? And then thirdly, your relative formula mass is the same idea, but you're looking at the relative atomic masses of all of your components in your ionic compound, and you're adding them together to come up with your relative formula mass. Now, you might be wondering to yourself, why haven't we ever referred to them in this particular manner before? And it just really comes down to a simplicity thing. In order to not have to always say the word relative in front of everything, it's almost like it's an understanding that when chemists are communicating about atomic masses, molecular masses, formula masses, that we know that it's relative to our understanding of the mole, which is with respect to carbon-12. I hope that makes sense. And so notice here that AR, MR, and MF have no units because they are relative terms. So this is not quite like AMU or our grams units, right? This is a specific way of coming up with these masses that have no units because they're relative to some other standard. Now, we can obviously talk about how we would calculate those things using units that we understand, like grams or AMU, but these are kind of the basis for how we got to using AMU or grams or something like that. All right. Molar mass, M, has the units of grams per mole. I'm pretty sure you guys knew that. So when we think about this, the mass of 1 mole of a species is going to be called its molar mass. And it has units of grams per mole, or IB likes to do this a lot. They're going to write things as gram times moles inverse. Now again, that still equals grams per mole, but that's how they like to write it. So if you see grams times moles inverse, know that it's talking about grams per mole, right? And so molar mass should be something that you guys are relatively familiar with. And so the last thing, or the application of the skills that you guys need to be able to do, can you guys calculate molar masses of atoms, ions, molecules, and formula units? I have a sneaking suspicion that the answer is yes to that question, but let's just take a look at a couple examples, and then I'll leave you guys with some problems to work on your own. All right, so to calculate the molar masses of something, you need to add up the atomic masses of the separate atoms that are given to you from the periodic table. So that's why your periodic table is so important. And so, like, for example, for carbon dioxide, now notice we've oversimplified here on some of these masses, but for one carbon atom, we know that has a molar mass of roughly 12. And then for oxygen, we know it has a molar mass of roughly 16. We got 2 of them, so 12 and 32. You add those together, you get 44 grams per mole as the molar mass of carbon dioxide. Pretty straightforward. Or if you look at something like methane, you've got 1 carbon atom, so 1 times 12 gives us a mass of 12. Hydrogen has a molar mass around 1. We got 4 of them, so 4 times 1 is 4. So methane has a molar mass that's around 16 grams per mole. Again, pretty straightforward calculations. I don't think I need to spend a lot of time looking at that. So as I close out this video, what I want you guys to do, calculate the molar masses for each of the following, right? You've got sodium bicarbonate, you got strontium cyanide, you got aluminum sulfite, you've got, I believe that's sucrose, and then you've got ammonium carbonate. Calculate their molar masses and make sure that you give your units in grams per mole. Okay. Thank you guys for stopping by. Thank you guys for watching this video. Hope it was helpful. Please make sure you fill out the Google form that's going to be associated with this video. And let me know if you have any questions, if you need me to go over anything, because I'll be more than happy to do that next time I see you guys in class. Thank you guys so much, and I'll see you guys soon.